Hari ini kita akan belajar dari kecelakaan-kecelakaan yang terjadi pada perusahaan petrokemikal. Materi training kali ini akan mempelajari apa saja hal-hal yang menyebabkan terjadinya kecelakaan sehingga kita dapat menghindarinya. Tipe-tipe kecelakaan yang akan kita pelajari meliputi fire, explosion, dan toxic release. Selain itu juga kita belajar terkait kecelakaan seputar valve, flange, dan switch.
Berikut ini adalah hal-hal yang perlu Anda perhatikan saat bekerja dengan valve, flange, dan switch. Pertama, pastikan sumber energi telah ditutup 100%. Sumber energi berupa sumber energi listrik, tekanan udara, tekanan hidrolik, ataupun aliran fluida. Kedua, lakukan penguncian sumber energi dan jangan lupa merilis terlebih dahulu sumber energi yang masih tersimpan dalam suatu sistem. Ketiga, lakukan testing sebelum memulai bekerja untuk memastikan bahwa sumber energi telah benar-benar terkunci dan terisolasi.
Pertama, pada tanggal 22 November 2016 terjadi kebakaran di ExxonMobil di daerah Louisiana, Amerika Serikat. Kebakaran terjadi dikarenakan isobutan rilis dari sela flange. Isobutan membentuk awan yang mudah terbakar dan meledak 30 detik setelah rilis. Kejadian ini menyebabkan 4 pekerja terluka. Penyebab dari kejadian ini adalah pekerja kurang terlatih dalam melakukan pekerjaan sehingga ia membuka valve yang seharusnya menjadi penahan rilisnya bahan kimia dari dalam pipa. Kedua, pada tanggal 13 September 2010 telah terjadi kebakaran di salah satu pabrik petrokemikal di dunia. Kejadian ini disebabkan oleh kebocoran heksan dari salah satu valve reaktor. Kebocoran tersebut menyebabkan level fluida dan tekanan drop yang selanjutnya diikuti ledakan besar. Kejadian ini menyebabkan 1 pekerja meninggal dunia dan 4 orang pekerja terluka. Penyebab dari kejadian ini adalah salahnya pemasangan blind screen yang mana seharusnya dipasang 2 namun pekerja hanya memasang 1 saja. Selain itu penyebab kedua adalah kurangnya monitoring proses yang menyebabkan tekanan tinggi di dalam reaktor menyebabkan aliran heksan menuju pipa yang salah. Sehingga menyebabkan kebocoran heksan dan membentuk awan yang mudah terbakar.
June 21st, 2019. The Philadelphia Energy Solutions Refinery in Philadelphia, Pennsylvania. At 4 a.m., flammable process fluid containing mostly propane, along with a small concentration of highly toxic hydrofluoric acid, or HF, escaped from the refinery's HF alkylation unit, likely through a ruptured pipe elbow. The alkylation unit produced components of high-octane gasoline. The leaking process fluid formed a large ground-hugging vapor cloud that surrounded some sections of the unit. 2 minutes later, the cloud ignited, causing a massive fire. A control room operator quickly took steps to prevent the release of additional HF by rapidly draining the unit's hydrofluoric acid to a special vessel designed to hold the acid in the event of an incident. At 4:15, during the ongoing fire, an explosion erupted in the alkylation unit. 4 minutes later, a second explosion occurred. At 4:22, a process vessel in the unit containing flammable hydrocarbons violently melted, causing the largest explosion. A large 38,000-pound fragment of the vessel flew across the Schuylkill River and landed on the river's opposite bank. 2 other fragments, one weighing about 23,000 pounds and the other about 15,500 pounds, landed inside the refinery. The fire burned for over 24 hours until it was finally extinguished the following day at about 8:30 a.m. 5 workers sustained minor injuries during the incident and response. The CSB is unaware of anyone experiencing health impacts from the hydrofluoric acid release. November 22nd, 2016. The ExxonMobil refinery in Baton Rouge, Louisiana. A fire erupted during maintenance activities, severely burning 4 workers. The fire occurred when operators inadvertently removed bolts that secured a piece of pressure-containing equipment to a type of valve known as a plug valve. When the operators then attempted to open the valve, it came apart and released flammable isobutane, which formed a vapor cloud that quickly ignited.
During our investigation, the CSB learned that the operators attempting to open the plug valve were following accepted practices within the refinery. Unfortunately, those practices lacked a safety hazard analysis, which needlessly put the workers at greater risk. The management of safety is critical to the protection of workers and the integrity of facility operations.
The fire at ExxonMobil's Baton Rouge refinery occurred in the sulfuric acid alkylation unit. There, isobutane and olefins are converted into a major component of gasoline through a reaction involving sulfuric acid. On the day of the incident, 2 operators were preparing to put a spare isobutane pump into service. To do so, the operators needed to open the pump's inlet plug valve. That plug valve was operated manually. A hand wheel and a piece of equipment called a gearbox were connected to the valve by a support bracket. The gearbox uses gears to make it easier to turn the valve stem into the open or closed position. The operators turned the hand wheel on the spare pump's inlet plug valve, but the gearbox was not working properly, and the valve would not open. When the gearbox was malfunctioning, it was an accepted practice in the alkylation unit for operators to remove the gearbox so that a pipe wrench could be used to turn the valve stem and open the valve. The gearbox was connected to the valve body by the support bracket using bolts. The operators removed 4 vertical bolts from the valve. But unknown to the operators, these bolts also secured a critical pressure-containing component of the valve known as the top cap. Approximately 3% of the numerous plug valves in the refinery's alkylation unit were designed so that the gearbox support bracket attached to the top cap. With this 30-plus-year-old design, removal of the gearbox support bracket can have catastrophic consequences. Approximately 97% of the valves were newer models with updated design that did not connect the gearbox support bracket to pressure-containing equipment, making it less likely to remove the incorrect bolts. With bolts removed from the top cap, one of the operators attempted to open the valve by rotating the valve stem with a pipe wrench, while the second operator stood by and observed. The valve immediately failed and came apart. Pressurized isobutane escaped from the valve, forming a flammable white vapor cloud. The 2 operators warned others in the area and directed them to evacuate. Approximately 2,000 pounds of isobutane released to the atmosphere. The vapor cloud likely found an energized welding machine roughly 70 feet away from the initial release and ignited. The resulting fire seriously injured 1 ExxonMobil employee and 3 contractors working in the area.
Our investigation into the incident revealed that management at the ExxonMobil Baton Rouge refinery were accepting of operators in the alkylation unit removing malfunctioning plug valve gearboxes without adequate written procedures or training.
The CSB also found that although refinery operators did receive training on hard-to-operate valves, the training did not specifically address how to remove an inoperable gearbox from the older plug valve model.
In our safety bulletin, we outlined 3 key lessons learned from this incident.
The first key lesson is to establish detailed and accurate written procedures for workers performing potentially hazardous work. This is especially important when different types of equipment or configurations exist that could cause confusion. A second key lesson is to provide training to ensure that workers can perform all anticipated job tasks. Training should include a focus on processes and equipment to improve hazard awareness and help prevent chemical incidents.
In our safety bulletin, we emphasize the hierarchy of controls. This is a method of evaluating safeguards to provide effective risk reduction. Within the hierarchy of controls, an engineering control, such as improved valve design, is more effective than a lower-level administrative control, such as a sign warning workers that the gearbox support bracket connects to pressure-containing components.
The CSB found that the 30-plus-year-old valves left in the refinery were not explicitly required to be updated to the safer design. That is because the older design did technically adhere to current industry standards, which call for items like gearboxes to be capable of removal without affecting pressure-containing parts. That could be accomplished by removing 2 horizontal bolts that connect the support bracket directly to the gearbox, rather than the 4 vertical bolts that secure the support bracket to the top cap. But on the day of the incident, the operator did not remove the 2 horizontal bolts.
The American Petroleum Institute, an industry trade association, says in its safety guidance for improving human performance to make it easy for people to do things right and hard for them to do things wrong. Updating all of the older valves to the safer valve design, as was done to approximately 97% of the valves in the alkylation unit, could have ultimately prevented this incident.
A third key lesson from the CSB's safety bulletin is to apply the hierarchy of controls to mitigate identified hazards. The CSB also found that in its most recent alkylation unit process hazard analysis, the refinery did not evaluate the human factors associated with valve operation and maintenance.
Had the refinery adequately addressed human factors in its most recent process hazard analysis, workers could have discussed difficulties with the removal of the plug valve gearboxes, prompting the company to identify potential hazards. As a result, the older valves could have been recommended for replacement, and the incident would have been avoided.
The safety management practices outlined in our bulletin could have prevented the fire in Baton Rouge. We urge companies to share and implement our key safety lessons at their facilities in order to prevent future injuries and property damage. Thank you for watching this CSB safety video.
For more information, please visit csb.gov.
Berikut ini adalah kebakaran yang terjadi saat dilakukan pekerjaan hot work, yaitu pengelasan. Sebelum melakukan pekerjaan, valve sudah ditutup namun tidak dipasang slip plate untuk memastikan tidak ada kebocoran dari valve. Saat pengelasan dilakukan, tidak lama kemudian terjadi ledakan dan melukai 2 pekerja. Pelajaran dari kejadian ini adalah implementasi LOTO sangat penting untuk mencegah terjadinya kecelakaan. Selanjutnya, 2 pekerja terluka saat melakukan pengelasan di atas tangki dikarenakan oleh ledakan dari dalam tangki melalui lubang di atas tangki. Saat air mulai diisi ke dalam tangki untuk pekerjaan hidrotes, gasolin di dalam tangki terdorong ke atas dan saat vapor dari bensin mencapai bagian atas tangki ledakan terjadi. Pelajaran dari kejadian ini adalah: pertama, kurangnya purging dan cleaning tangki sebelum dilakukan hidrotes. Kedua, kurangnya pengawasan, selama hidrotes dilarang ada pekerjaan di sekitar tangki.
Inadequate isolation, multiple damage. The production sequence of a factory involved the operation of 3 reactors, which could work in series or parallel to increase production capacity. However, it was noticed that one of them was producing out of specification. The leadership team then decided to pause the operation of this single reactor to carry out improvement services. A reactor was prepared for maintenance and washed out. The previous solution was drained, and a specific washing was carried out to clean the reactor. An operator and a third-party maintenance worker were discussing the necessary fittings close to the equipment to verify adversities in place. To perform the necessary adjustments, no welding needed to be done, and no entry was required. So it was decided not to slip plate off the reactor, but to rely on valve isolation. The 3 automatic on-off valves supplying the reactor were closed by the panel operator through the control room. A third-party mechanic was directed to cut the tank drain line to allow for the installation of new equipment. He uses a grinder to carry out the job, supervised by an operator from that area. However, after a few moments later, they identify a strange noise and started to leave the spot, but they can't escape in time. Before they managed to leave the place completely, the reactor was blown off and killed the 2 men. A shockwave caused by the explosion knocked the 2 workers to the ground. Unfortunately, they couldn't resist the injuries. Fire and smoke were seen for about 15 minutes until causes were addressed. So what happened? It was estimated that 7 kilograms of hydrocarbon vapor could have caused the explosion. Some flammable vapor leaked from the nearby raw material tanks through the closed valves into the reactor and was ignited by a high-speed abrasive wheel, which was being used to cut through one of the pipelines attached to the vessel. As the valves mistakenly used as blocking were located at a significant height, a local inspection was not carried out to test the effectiveness of the isolation. After the accident, demonstration cuts were made in the workshop. It was found that as the abrasive wheel broke through the pipe wall, a small flame occurred, and the pipe itself glowed dull red. The explosion could have been prevented by isolating the reactor by slip plates or physical disconnection. This incident and the others described show that using only valves as LODO for isolation are not good enough. We must never underestimate checking the effectiveness of the isolation before releasing the permit to work. If you found the content interesting, please consider subscribing to our channel so we can make more videos.
A new tank was being filled with water for hydrostatic testing. 2 mechanics were working at the stairs near the roof, finishing the handrails, using angle grinders to polish the structure. Hydrostatic testing is a process in which components of a system are tested for resistance and leakage by filling equipment with a pressurized liquid. It serves to identify material failures or tank misassembly. The responsible operator starts the field activities. Firstly, he opens the switch and activates the pump start button. Immediately after he opens the discharge valve, allowing water to enter the tank. But a few hours later, something unexpected happens. an explosion occurs, injuring 2 mechanics working on the tank, throwing them against the handrails. What happened? The tank had been filled with water through a pipeline, the same pipeline that contained a few liters of gasoline left over from the previous service. So the gasoline was flushed into the tank and floated over the water. And the high ambient temperature caused the gasoline to evaporate. The mechanics performing the hot work eventually ignited the gasoline vapor. What have we learned? Apart from the fact that the piping has not been purged and mechanically cleaned prior to testing, which already is a serious cause of this event, no one should be allowed to work on the tank during a hydrostatic test. One of the reasons for filling the tank with water is to ensure that foundations are strong enough. If you could know that before, there is no need to perform the test. People should be removed from the surroundings and the area should be isolated in case these structures are not strong. Berikut ini adalah ledakan dan kebakaran yang terjadi di pabrik kimia TPC Group di Port Neches, Texas, pada 27 November 2019. Ledakan tersebut menyebabkan menara proses terlempar ke udara dan mendarat di dalam fasilitas. Kejadian ini menyebabkan 3 orang terluka dan kerusakan properti senilai $450 juta. Penyebab kejadian adalah kegagalan untuk mengidentifikasi bahwa pompa yang tidak berfungsi lagi di dalam unit butadin menyebabkan terjadinya dead leg yang berbahaya. Oleh karena itu, analisa bahaya proses harus diimplementasikan dengan baik. Selanjutnya, pencampuran yang tidak disengaja selama operasi loading-unloading bahan kimia dapat menimbulkan gas berbahaya. Pada tanggal 21 Oktober 2016, seorang transporter bahan kimia secara tidak sengaja meloding asam sulfat ke jalur pipa sodium hipoklorit. Kejadian tersebut menyebabkan timbulnya kepulan awan gas klorin yang berbahaya hingga mencapai lokasi penduduk setempat. Pelajaran dari kejadian ini adalah setiap jalur untuk loading bahan kimia harus dibedakan, diberikan keterangan, dan selalu dilakukan pengawasan saat kegiatan loading.
October 26, 2019, the Aghorn Operating Incorporated water flood station near Odessa, Texas. One Aghorn employee succumbed to toxic hydrogen sulfide gas that had escaped through a damaged pump. His spouse was also fatally injured by the hydrogen sulfide gas while searching for him at the facility after he didn't return home.
Hydrogen sulfide is prevalent throughout oil and gas formations in the United States and at many oil and gas production and processing facilities. Hydrocarbons from the Permian Basin in particular are known to contain high concentrations of hydrogen sulfide that are immediately dangerous to life or health. Our review of this event is about the unfortunate loss of 2 lives. But the lessons from this incident affect the multitude of other oil and gas facilities throughout the country that handle toxic hydrogen sulfide. This incident was both tragic and unnecessary. We urge companies operating oil and gas facilities to understand the findings from this investigation and implement appropriate safeguards and training. We need to work together to ensure that our workers and community members return home safely each and every day.
The Aign waterflood station is used as part of a process to extract oil from underground reservoirs in West Texas. Oil extraction starts at an oil well, where pump jacks are used to lift oil from underground reservoirs. Reservoirs in West Texas also contain hydrogen sulfide, a toxic gas which comes to the surface with the oil that is extracted. The oil comes out of the ground with some water in it. To remove the water, the mixture is fed to a tank battery. As the oil and water mixture sits in the tanks, the water separates from the oil. The oil is then transported for further processing. The water is pumped through pipelines to the waterflood station. It is now called produced water because it can contain residual oil and other contaminants, such as toxic hydrogen sulfide gas. At the waterflood station, the produced water flows into a large storage tank called a suction tank. The water then enters a building called the pump house. There, pumps are used to pressurize the produced water and inject it back into the oil field through injection wells. The injected water increases reservoir pressure and displaces the oil, allowing a larger quantity of oil to be extracted. At the time of the incident, there were 2 pumps in the pump house. The pump house also contains a control room from which employees run the station. Typically, the station is not continuously occupied. Instead, an Aign employee called a pumper visits twice per day to record meter readings and inspect equipment. If there is an equipment problem and a pumper is not at the station, an alarm system triggers an automated phone call to the pumper. It is then the pumper's responsibility to acknowledge the alarm and go to the station to determine what is causing it. The station was also equipped with a hydrogen sulfide detection and alarm system that would trigger a separate automated phone call to the pumper on duty if it detected dangerous levels of the toxic gas. The system would also illuminate a rotating red beacon light on top of the pump house. But the CSB found that this critical detection and alert system was not functional on the night of the incident. At 6:38 p.m. on October 26th, the waterflood station's control system activated an oil level alarm on a pump. 5 minutes later, the phone system called an Aign pumper, alerting him of a pump malfunction of some kind. The pumper drove to the waterflood station. The hydrogen sulfide beacon light was not illuminated when the pumper arrived at the waterflood station or at any time for the rest of the night. The pumper parked near the waterflood station, leaving his personal hydrogen sulfide monitor inside his truck. The pumper went into the control room, where the control system indicated the alarm was for pump number 1. The pumper prepared for work on pump number 1. The pump, which could automatically start when enough water was available to pump to the injection wells, was still connected to its power source. The pumper did not de-energize the pump. The pumper then walked to the pumps. He closed pump number 1's discharge valve and partially closed the pump's intake valve. While the pumper was near the pump, he was overcome and fatally injured by toxic hydrogen sulfide gas. After the incident, the CSB found that a plunger on the pump had shattered, which had allowed water containing hydrogen sulfide to escape from the pump into the pump house where the pumper was working. Due to limitations of available evidence, the CSB was unable to determine whether the pump failure and water release occurred before the pumper arrived at the facility or if the pump automatically turned on while the pumper was closing valves. After several hours, when the pumper did not return home, his spouse drove with their 2 children to the station to check on him. She entered the waterflood station facility and searched for him. She soon found him on the floor in the pump house. She then was also overcome and fatally injured by the toxic hydrogen sulfide gas. A short time later, emergency responders approached the pump house. They detected a very strong smell of hydrogen sulfide. This required them to set up the command post outside the front gate of the facility and wear self-contained breathing apparatus. They found the pumper and his wife deceased inside the pump house and water spilling from pump number 1. The responders rescued the 2 children who were inside the spouse's car. Working with Aghorn employees, they were able to stop the water release the following morning.
During our investigation, we identified 6 major safety issues at the facility.
One of the 6 safety issues identified was that the pumper was not equipped with his company-issued personal hydrogen sulfide detection device inside the pump house on the night of the incident. When the pumper's personal hydrogen sulfide detector was located in his work truck, it was found to be in an alarm state, meaning it had detected dangerous levels of hydrogen sulfide. The potential for a hydrogen sulfide release was a known hazard at the water flood station, as indicated by the posted signage and a safety pamphlet provided to all employees. However, there was no evidence that Aghorn management required use of personal hydrogen sulfide detectors or adequately trained employees that equipment malfunctions could indicate a toxic hydrogen sulfide release.
Companies should ensure workers always use the required safety equipment, such as personal detectors, when entering a potentially hazardous area. Regular training and posting signs will help remind employees to use their safety equipment every time.
The second safety issue CSB investigators discovered is that at the time of the incident, Aghorn did not have any written lockout-tagout policies or procedures, but relied on verbal procedures without formalized training. On the night of the incident, the pumper did not properly perform lockout-tagout to de-energize the pump before performing work on it. Instead, he started to close the pump's valves while the pump was still configured to be automatically operated by the control system. As a result, the control system automatically turned the pump on, and water containing hydrogen sulfide was able to escape from the pump when the discharge valve was closed.
Companies must have written lockout-tagout policies and procedures that instruct to isolate all possible sources of energy before employees perform work on equipment. Companies also need to routinely train employees on the lockout-tagout procedures.
The third safety issue identified by the CSB was that ventilation inside the pump house was inadequate, leading to fatal concentrations of hydrogen sulfide gas within the building. The CSB found that the pump house could be ventilated by 2 bay doors, exhaust fans, and natural vents on each of the 4 outside walls. Due to the limitations of available evidence, the CSB was unable to confirm whether the exhaust fans were operational at the time of the incident. The 2 bay doors were approximately 60% open, but this was not enough to adequately ventilate the building. And the CSB's investigation could not find any evidence that Aghorn assessed the pump house to ensure it could be properly ventilated, despite the potential for a hydrogen sulfide release to occur inside.
Companies should evaluate any buildings that contain equipment handling toxic gases and determine if the building is necessary. If it is, companies should ensure the building is equipped with a functioning toxic gas detection and alarm system and a ventilation system designed for the release of toxic gases. If the building is not necessary for the operation, a safety assessment should be conducted to determine if removal of the building or relocation of the equipment can prevent confinement of any toxic gas releases.
The fourth safety issue noted by the CSB was the lack of a robust safety management program at Aghorn. Comprehensive safety management practices include risk identification, assessment, mitigation, and monitoring of design, procedures, maintenance, and training. Safety management practices are an essential element of protecting workers and non-employees from toxic gases at chemical plants. At Aghorn, there were no operational, training, testing, and maintenance procedures or records, other than items such as a cell phone use policy and a pamphlet on the hazards of hydrogen sulfide. These items were not sufficient to prepare employees for potential encounters with hazards inherent to their work.
At facilities that handle toxic gases, companies must develop and implement a robust safety management program to protect workers and non-employees from exposure to toxic gas.
The CSB identified a fifth safety issue at Aghorn, which was a non-functioning hydrogen sulfide detection and alarm system. Some of the facility's detectors were set to a testing mode, which prevented them from sending an alarm signal. And other sensors that were correctly set up were unable to send a signal to the control room. As a result, the pumper was not warned of the toxic hydrogen sulfide, either through a telephone alert or illumination of the red pump house beacon light.
At facilities that handle toxic gases, gas detection and alarm systems must be adequately designed, maintained, and tested. Alarms should clearly alert to the hazard through visual and audible indications. Visual indications should be discernible during any time of day. Signs alerting that the facility handles toxic gas should be posted in clear view, legible at day and night, and should be well maintained.
And finally, the sixth safety issue discovered by the CSB at Aghorn was deficient site security. Per Aghorn's informal policy, when an Aghorn employee is working at the facility, the access gates are normally left unlocked. On the night of the incident, this practice allowed the pumper's spouse to drive directly to the water flood station and enter the pump house, where she was also fatally injured.
Effective site security must be in place to prevent non-employees from accessing hazardous areas.
As a result of its investigation, the CSB made the following recommendations to Aghorn Operating Incorporated for safety improvements at all water flood stations where the potential for exposure to dangerous levels of toxic hydrogen sulfide gas exists. These include mandate the use of personal hydrogen sulfide detection devices, develop a site-specific, formalized, and comprehensive lockout-tagout program for each facility, commission an independent and comprehensive analysis of each facility to examine ventilation and mitigation systems, develop and demonstrate the use of a safety management program that includes a focus on protecting workers and non-employees from hydrogen sulfide, ensure that hydrogen sulfide detection and alarm systems are properly maintained and configured, and develop site-specific detection and alarm programs and associated procedures. Ensure that the hydrogen sulfide detection and alarm system designs employ multiple layers of alerts unique to hydrogen sulfide, and develop and implement a formal, written, site-specific security program to prevent unknown and unplanned entrance of those not employed by Aghorn. The CSB also recommended that OSHA issue a safety information product that addresses the requirements for protecting workers from hazardous air contaminants and from hazardous energy. And the agency made a recommendation to the Railroad Commission of Texas to develop and send a notice to all oil and gas operators that fall under its jurisdiction that describes the safety issues outlined in the CSB's report.
Aghorn's safety deficiencies identified by the CSB through this investigation can be corrected. OSHA implementation of CSB's recommendation would send a strong message to the chemical industry of their priority to protect workers from the risks of chemical releases. This recommendation would not be limited to hydrogen sulfide, but would encompass workers across chemical facility domains. The implementation of CSB's recommendation to the Railroad Commission of Texas would make significant strides to educating the chemical industry and address the majority of water flood stations that involve hydrogen sulfide. Many of these companies are small and involve employees that work alone, and in many cases in remote locations. This recommendation would also go a long way to help educate those companies that may not be on the leading edge of safety. This tragic accident did not need to happen. This is a call to action for all companies, large and small, to step up to the plate, to prioritize the safety of your workers and your community.
For more information about the CSB's Aghorn investigation, please visit csb.gov. October 21st, 2016. The MGPI processing facility in Atchison, Kansas. An unintended chemical reaction resulted in a dense cloud containing toxic chlorine gas and other chemicals that drifted into the community, leaving over 140 people with reported injuries. The incident occurred during a routine chemical delivery when two incompatible chemicals, sulfuric acid and sodium hypochlorite, were inadvertently mixed, forming the toxic cloud.
Delivery and unloading operations may be perceived as simple compared to other processes at chemical facilities. But because these activities can involve large quantities of chemicals, the consequences of an incident can be severe. Our case study on the MGPI incident stresses that facilities must pay careful attention to the design and operation of chemical transfer equipment to prevent similar incidents.
The MGPI facility produces distilled spirits, specialty wheat proteins, and starches. The incident occurred in a section of the plant that uses sodium hypochlorite, or bleach, as well as sulfuric acid. These two chemicals, when combined, can form chlorine gas and other chemical compounds. On the morning of the incident, a truck from a chemical distribution company, Harcross Chemicals, arrived at MGPI to complete a routine delivery of sulfuric acid. After reviewing paperwork in the control room, an MGPI facility operator escorted the driver to a locked loading area. There, chemicals are transferred from trucks into the facility through piping, called fill lines, to several large storage tanks in an outdoor tank farm. The MGPI operator unlocked the sulfuric acid fill line for the driver to connect the truck's unloading hose. The operator remembers pointing out the correct fill line to the driver before he returned to his workstation. The driver, however, does not recall hearing the operator identify the fill line. Unknown to the operator, the sodium hypochlorite fill line was also unlocked, and the two lines, which were only 18 inches apart, looked similar and were not clearly marked. The driver connected his truck's sulfuric acid hose to the sodium hypochlorite line, and sulfuric acid began flowing inside. He then returned to the cab of his truck. Shortly before 8 a.m., a greenish-yellow gas began flowing from the bulk tank of sodium hypochlorite. The driver noticed the cloud in his truck's side view mirror and attempted to return to the connection area to turn off the flow of sulfuric acid, but the gas overwhelmed him. He then ran to the passenger side of the truck to close a valve that could halt the flow, but he was prevented from doing so by the gas. Instead, he ran away from the cloud and escaped to a separate area of the facility. At about the same time, toxic gases entered the facility control room through the building's ventilation system. MGPI operators preparing for shift change in the control room were immediately overcome by the toxic gas. Because the operators had a practice of locking respirators between shifts, some were unable to access their respirators before evacuating the building. With no other way to stop the flow other than closing manual valves on the fill line or truck, or by triggering one of the truck's emergency shutoffs, the sulfuric acid continued to enter the sodium hypochlorite tank for nearly 45 minutes until emergency responders shut down the flow. Approximately 4,000 gallons of sulfuric acid combined with 5,800 gallons of sodium hypochlorite, causing a large, dense cloud containing chlorine gas, which soon drifted off-site. MGPI employees were evacuated from the site, and 11,000 Atchison citizens were advised to either shelter in place or evacuate. Over 140 people, including MGPI employees, emergency responders, the truck driver, and members of the public, sought medical attention, some requiring hospitalization.
Chemical distribution takes place on a massive scale in the United States. According to a study by the National Association of Chemical Distributors, more than 39.9 million tons of product were delivered to customers every 8.4 seconds in 2016. The CSB is concerned that there are many opportunities for incidents like the one at MGPI to occur.
John Hennigan is director of the Pipeline and Hazardous Materials Safety Administration's Hazardous Materials Safety Southern Region Enforcement Office.
According to our data from 2014 through 2017, unloading incidents involving hose connections to incorrect tanks occur frequently. These incidents are often quite serious because of the large amount of chemicals involved. Most commonly, the incidents involve compatible materials and result in tank overfills. Incidents similar to the one at MGPI, where two incompatible materials are inadvertently mixed and result in a chemical reaction, occur less often, but are nonetheless problematic. Since 2014, 8 incidents similar to MGPI have occurred. These incidents resulted in 44 injuries and the evacuation of 846 people.
In its case study on the MGPI incident, the CSB identified several human factors deficiencies which influenced how the operator and driver interacted with the chemical transfer equipment.
Chemical facility operators and delivery drivers often work directly with chemical transfer equipment for loading and unloading operations. The study of human interactions with process equipment, called human factors, should be carefully considered when identifying hazards, particularly because chemical delivery drivers may not be familiar with the facility's equipment.
For example, at MGPI, the CSB found that the close proximity of the sulfuric acid fill line to the sodium hypochlorite fill line increased the likelihood for workers to make an incorrect connection during chemical unloading. The CSB also discovered that the two fill lines looked and functioned identically, using the same type of connections. Lastly, the CSB found that of the 5 fill lines in the unloading area, only one was labeled at the point where the hose connected.
A key lesson from our case study is for facilities to evaluate chemical unloading equipment and processes, and implement safeguards to reduce the likelihood of an incident. This should be done while taking into account human factors issues that can impact how facility operators and drivers interact with that equipment.
This can include physically separating fill lines by a discernible distance, selecting hose couplings and fill line connections with unique shapes or colors for each type of chemical, and ensuring that fill lines are properly labeled. Also, during its investigation, the CSB found that at the time of the incident, MGPI did not have instrumentation that could automatically shut down the transfer of chemicals from the unloading area in the event of a process deviation, since the only ways to shut down the transfer of sulfuric acid to the sodium hypochlorite tank required human interaction and were located within areas affected by the release. There was no way for workers without proper personal protective gear to stop the flow once it began.
Another key lesson from our case study is for facility management to evaluate their chemical transfer equipment and processes, and where feasible, install alarms and interlocks in the process control system that can shut down the transfer of chemicals in an emergency.
Finally, the CSB found that MGPI's procedures were not aligned with their work practices. On the day of the incident, the operator was not present when the transfer hose was connected to the fill line, even though the company's procedures state that operators must verify the connection and that the operator should be the one to open the fill line valve. But the CSB discovered that some operators were not aware of these steps in the procedures, and that it was their practice to have drivers open the fill line valve, thinking this would be safer, since drivers wear personal protective equipment in the event of a release.
A third key lesson from our case study is for facilities to work with chemical distributors to conduct a risk assessment and then develop and agree upon procedures for chemical unloading to ensure responsibilities are clearly defined.
As the MGPI incident demonstrates, although unloading operations are relatively simple compared to many of the complex processes taking place in chemical facilities, the consequences can greatly impact workers and surrounding communities due to the large amounts of chemicals transferred during deliveries.
Chemicals are transported and delivered every day all around us. Because these deliveries are so common, the CSB strongly urges the managers of facilities and distributors to review and adopt the key lessons from our case study and work together to prevent future incidents like the one at MGPI. Thank you for watching the CSB safety video.
For more information on the CSB's investigation, please visit csb.gov.
Berikut ini adalah kejadian kebakaran dan ledakan yang mana sel dari reboiler pecah secara dahsyat sehingga menyebabkan boiling liquid expanded vapor explosion, BLEVE, dan kebakaran. Insiden ini terjadi pada tanggal 13 Juni 2013 di pabrik petrochemical William Olefin Geismar, Amerika Serikat. Insiden tersebut terjadi pada saat kegiatan operasional non-rutin yang memasukkan panas ke dalam reboiler yang sedang offline dan diisolasi dari alat pelepas tekanannya. Panas tersebut meningkatkan suhu campuran propana cair yang secara tidak sengaja berada di dalam reboiler karena terdapat valve yang passing. Hal tersebut mengakibatkan peningkatan tekanan yang dramatis di dalam bejana. Sel reboiler pecah secara dahsyat, menyebabkan boiling liquid expanded vapor explosion, BLEVE, dan kebakaran yang menewaskan satu pekerja dan 167 orang lainnya melaporkan cedera. Kekurangan dalam penerapan Management of Change, MOC, Pre-Startup Safety Review, PSSR, Program Proses Hazard Analysis, PH, yang menyebabkan insiden tersebut. Berikutnya adalah kejadian kebakaran di Louisiana, Amerika Serikat. Pada tanggal 22 November 2016, terjadi pelepasan isobutana di unit alkilasi asam sulfat di kilang ExxonMobil di Baton Rouge yang mengakibatkan 4 pekerja luka berat dan 2 lainnya luka-luka. Insiden ini terjadi saat pemeliharaan kecil pada saluran isobutana yang mudah terbakar namun gagal, sehingga melepaskan isobutana ke dalam unit yang terbakar. Untuk mencegah kejadian ini, pelatihan harus mencakup fokus pada proses dan peralatan untuk meningkatkan kesadaran akan bahaya dan membantu mencegah insiden bahan kimia.
June 13th, 2013, the Williams Geismar Olefins plant in Geismar, Louisiana, a heat exchanger violently ruptured, causing an explosion and fire that killed 2 workers. The Chemical Safety Board launched an investigation, Process Safety Management Program deficiencies at Williams, which set the stage for the incident. In particular, the CSB found that the heat exchanger that failed was completely isolated from its pressure relief valve. When pressure inside the heat exchanger dangerously increased, there was nothing to stop a catastrophic rupture. The Williams Geismar Olefins plant is located in Geismar, Louisiana. The plant produces ethylene and propylene. These are chemicals used in the petrochemical industry to make a variety of products, including plastics and antifreeze. Within the Williams process is a distillation column called the propylene fractionator. It separates a mixture of propane and propylene. Heat exchangers called reboilers supply heat to the fractionator to boil the propane and propylene mixture, which is essential to the separation process. The reboilers are shell and tube heat exchangers. Hot water flows through the tubes, heating and vaporizing propane that flows through the shell and back to the propylene fractionator. The water that flows through the tubes contains a small amount of oily tar, which condenses into the water earlier in the process. Over time, the oily tar from the water builds up on the walls of the reboiler tubes. This buildup is called fouling. Fouling reduces the efficiency of the reboilers. Periodically, the reboilers must be shut down to clean the tubes. The original propylene fractionator design had both reboilers running simultaneously, but in that configuration, the fractionator had to be shut down when a reboiler fouled and needed cleaning. To prevent shutdown of the propylene fractionator each time the reboilers needed to be cleaned, in 2001, new valves were installed on each reboiler to allow for operation of only one at a time. The other reboiler is on standby, clean and ready for use. But unforeseen at the time, these valves introduced a serious hazard. They isolated the standby reboiler from its protective pressure relief valve, located on top of the fractionator. On June 13, 2013, during a daily meeting with operations and maintenance personnel, the Williams plant manager noticed that the water flow rate through the operating reboiler had dropped gradually over the past day. The operations supervisor informed the group he would try to identify the problem. He went into the plant to evaluate the water flow rates. The operations supervisor informed several personnel that fouling within the operating reboiler could be the problem, and they might need to switch the reboilers. He attempted to meet with his manager so they could get the necessary maintenance and operations personnel involved who would perform the work. But his manager was not available. The operations supervisor returned to the field. The CSB determined that at 8:33 a.m., the operations supervisor likely opened the water valves on the standby reboiler. Hot water began flowing inside. The valves blocking the reboiler from its protective pressure relief valve remained closed. But unknown to the operations supervisor, the standby reboiler contained flammable liquid propane that had accumulated during the 16 months the reboiler was out of service. The hot water quickly heated the liquid propane confined inside of the reboiler, and pressure dangerously increased. Just 3 minutes later, the reboiler violently ruptured. Propane exploded from the reboiler and ignited to create a massive fireball. The explosion killed the operations supervisor and an operator working nearby. 167 Williams employees and contractors reported being injured. During its investigation, the CSB found that prior to the explosion, the standby reboiler had been out of service for over a year, isolated from the process by closed block valves. But during this 16-month period, liquid propane unintentionally entered the shell of the reboiler, perhaps through a mistakenly opened valve or a leaking block valve. The CSB determined that when the operations supervisor opened the hot water valves to the standby reboiler, the propane liquid trapped inside was heated and expanded in volume to completely fill the reboiler shell. This caused pressure to dramatically increase until the reboiler ruptured. The CSB discovered that in the 12 years leading to the incident, a series of process safety management program deficiencies caused the reboiler to be unprotected from overpressure. When Williams installed the process block valves on the reboilers in 2001, they performed a management of change review to identify how this action affected the safety of the process. The CSB found, however, that Williams did not identify that the new valves could isolate the reboilers from their protective pressure relief valve. Companies are required to conduct a management of change review before making equipment changes, so they may consider the impact of that change on the safety of the process. But the CSB discovered that Williams conducted the management of change review after the process was already operating with the new valves. After the 2001 reboiler valve installation, Williams also performed a pre-startup safety review, as required by regulations. But the CSB found that Williams reviewers did not respond to key process safety questions on the form. One of those questions asked, are pressure relief systems in place and operational? That answer was left blank. The CSB found that in the following 10 years, Williams performed 3 process hazard analyses, or PHAs, in 2001, 2006, and 2011. None of the PHAs sufficiently identified or controlled the reboiler overpressure hazard. An internal recommendation from the 2006 PHA stated, consider locking open at least one of the manual valves associated with each of the propylene fractionator reboilers. While that recommendation was marked as complete, the CSB found that it was not implemented as intended. And the CSB found that Williams failed to develop a procedure for activities performed on the day of the incident. As fouling in the quench water system was a known issue, Williams should have had a written procedure to assess fouling and switch the reboilers. Furthermore, the company could have established a routine maintenance schedule to prevent extensive fouling in the first place. To prevent future incidents and further improve process safety at the Geismar plant, the CSB recommended that Williams conduct safety culture assessments that involve workforce participation and communicate the results in reports that recommend specific actions to address safety culture weaknesses. Develop a robust safety indicators tracking program that uses the data identified to drive continual safety improvement, and perform comprehensive process safety program assessments to thoroughly evaluate the effectiveness of the facility's process safety programs. In its case study, the CSB encourages companies from across the country to review and incorporate the safety lessons and recommendations from the Williams Geismar plant investigation within their own facilities.
Berikut ini adalah kebakaran yang terjadi pada salah satu perusahaan petrokemikal di Curaray, Texas. Kondisi tekanan tinggi terjadi di dalam reaktor sehingga mengaktifkan sistem pelepas tekanan darurat reaktor. Pada saat bersamaan mengeluarkan uap etilen yang mudah terbakar melalui pipa ke area tempat sejumlah kontraktor bekerja. Lebih dari 2.300 pon etilen dilepaskan dalam waktu sekitar 3 menit. Diketahui terdapat pekerjaan pengelasan di dekat reaktor tersebut, sehingga menyulut uap yang mudah terbakar. Penyebab dari kejadian ini adalah kombinasi dari elemen-elemen sistem manajemen yang tidak efektif sehingga menimbulkan kebakaran. Selanjutnya, berikut ini adalah kecelakaan fatality yang terjadi di salah satu perusahaan minyak di Texas. Pada tanggal 26 Oktober 2019, seorang karyawan Agorn, Pumper A, merespon level oli pompa alarm di lokasi kerjanya. Menanggapi alarm tersebut, Pumper A bekerja untuk mengisolasi pompa dari proses dengan menutup katup pelepasan pompa dan menutup sebagian katup hisap pompa. Pumper A tidak melakukan loto terlebih dahulu untuk mengisolasi pompa satu dari sumber energi sebelum melakukan pekerjaan pada pompa. Beberapa saat pada malam kejadian, pompa otomatis menyala dan air yang mengandung hidrogen sulfida, H2S, gas beracun, dilepaskan dari pompa. Pekerja langsung terjatuh karena menghirup gas hidrogen sulfida. Pekerja tersebut tidak memakai gas detektor personal sehingga tidak mengetahui adanya gas H2S yang terlepas saat bekerja. Istri korban yang sudah lama menunggu di rumah merasa curiga dan menyusul suaminya ke lokasi kerja. Di sana ia mendapati suaminya tergeletak dan ia pun menyusul suami ke dalam untuk menolongnya. Namun sang istri akhirnya ikut meninggal bersama dengan suaminya karena menghirup gas beracun yang sama.
May 19th, 2018, the Curaray America chemical plant in Pasadena, Texas. The plant manufactures Eval, a copolymer made from ethylene and vinyl alcohol. Eval is used in food packaging and storage containers. Curaray shut down the Pasadena plant on April 6th for a maintenance turnaround and to install various equipment upgrades. By May 18th, Curaray operations personnel were taking steps to bring one of 4 reactors back online. The reactor, known as Eval Reactor 2, looked similar to the others, but had a lower maximum design pressure of 740 psi. The design pressure of the other 3 reactors was 1150 psi. The reactor already had liquid methanol and ethylene vapor inside as operators began incrementally raising the reactor system pressure. They did so by adding additional ethylene vapor. Pressure was raised in order to reach the target pressure necessary for the reactor to start up, while also checking for leaks. In the meantime, chilled liquid from the plant's newly installed refrigeration system was circulating through the reactor's heat exchanger. After 11:20 p.m., the reactor pressure, together with the low temperature from the chilled liquid, created conditions that allowed the ethylene gas in the reactor to condense to liquid. This caused the temperature in the reactor to decrease. Around 7 a.m. on May 19th, a supervisor noticed the low temperature in the reactor and instructed operators to stop circulating the chilled liquid through the heat exchanger. The reactor was surrounded by a heat transfer jacket, which uses water to control the temperature inside the reactor. To further help warm the reactor, Carrare personnel periodically added steam to the jacket, increasing the temperature of the water. As the temperature of the reactor increased with each injection of steam to the heat transfer jacket, some liquid ethylene inside the reactor vaporized. This raised the pressure inside the reactor. By about 8:45 a.m., the reactor reached the target operating pressure of nearly 600 psi, but pressure continued to increase. Around 9 a.m., the pressure reached 640 psi, and the high pressure alarm went off. A board operator responded by periodically opening a pressure control valve to send some of the vapor inside the reactor to a flare. The board operator was concerned about exceeding environmental emissions limits for the flare. As a result, he did not fully open the pressure control valve. He was also focused on other startup activities and did not realize the valve was not open as much as it needed to be to bring the pressure under control. Pressure inside the reactor continued to climb. Shortly after 10 a.m., operators initiated the next step in the startup. At that time, a new board operator took over and noticed the pressure in the reactor was over 700 psi. But the operator did not recall that this reactor had a maximum design pressure of 740 psi. He thought it could withstand higher pressure like the others. Like the first board operator, the new operator only partially opened the pressure control valve, not realizing how dangerously close the pressure was to the reactor's limit. The partially open control valve was not enough to relieve the pressure in the reactor. Shortly before 10:30 a.m., the emergency pressure relief system activated. High-pressure ethylene vapor discharged from the reactor into the atmosphere. It was released horizontally toward an area where many people were working, rather than vertically to a safe location. Soon after, a nearby welding machine likely ignited the vapor, and a large fire erupted. 23 people were injured, many as they urgently tried to evacuate. The ethylene-fueled fire stopped after approximately 3 minutes, when the emergency relief valve closed as pressure in the reactor normalized. In total, over 2,000 pounds of ethylene was ejected to the atmosphere. For more information, visit csb.gov. November 27th, 2019, the TPC Group chemical plant in Port Neches, Texas. A release of highly flammable butadiene caused a series of explosions that could be felt up to 30 miles away. The blast destroyed a portion of the TPC facility, damaged nearby homes and businesses, and prompted a mandatory evacuation of residents living within 4 miles of the plant. Several workers and members of the public reported injuries, and fires burned at the facility for over a month.
The incident at TPC was the result of a known hazard where popcorn polymer grew and formed inside equipment that was poorly managed and controlled at the facility. Gaps in industry good guidance on the management of popcorn polymer formation played a role. The result was a catastrophic incident that disrupted life at the facility as well as the local community.
TPC is a petrochemical manufacturing company with several facilities along the Gulf Coast of Texas and Louisiana. At the time of the incident, the company produced butadiene at its Port Neches plant. Butadiene is used as a building block in the production of a wide range of products, but is most commonly used to produce synthetic rubber. It is a highly reactive chemical, which if not properly managed, can lead to serious hazards. For instance, in the presence of oxygen, high-purity butadiene can undergo reactions to form a solid substance known as popcorn polymer. If popcorn polymer accumulates and grows inside process equipment, it can lead to very high pressure and ultimately cause the equipment to rupture. On August 4th, 2019, a worker performed a routine operation in TPC's butadiene unit. As part of that operation, the worker shut down a primary pump that was part of the butadiene production process. When the worker tried to restart the pump, it would not operate. The primary pump was sent for repair and remained out of service from that date forward. A spare pump was used to continue operations. The inoperable pump created a significant dead leg, which is an area of piping that is open to the process but does not have any material flowing through it. The CSB determined that over the next 114 days, popcorn polymer began to form and accumulate within the dead leg. But the CSB could not find evidence that anyone at TPC recognized the hazard created by the dead leg. At 12:54 a.m. on November 27th, excessive popcorn polymer buildup caused the dead leg piping to suddenly rupture. Approximately 6,000 gallons of liquid, primarily composed of butadiene, emptied through the ruptured piping in less than a minute. The liquid vaporized upon release to the atmosphere, forming a flammable cloud. 3 nearby workers were startled by the rupture. They immediately recognized the danger and quickly departed as the vapor cloud grew. In just 2 minutes, the flammable vapor cloud found an ignition source and exploded. The resulting pressure wave destroyed parts of the facility and injured 2 TPC employees and a security contractor. The blast damaged nearby homes and buildings and was reportedly felt up to 30 miles away. Local officials stated 5 residents reported minor injuries. At least 2 additional explosions occurred following the initial blast. Some of the piping damaged by those explosions could not be isolated. As a result, flammable process fluid continued to escape from ruptured equipment, and smaller contained fires burned for more than a month. At 10:09 a.m. on January 4th, 2020, the TPC Incident Command confirmed that all fires were finally out. The Chemical Safety Board launched an investigation into the incident at TPC and found 4 key safety issues contributed to the incident. They are dead leg identification and control, process hazard analysis, action item implementation, control and prevention of popcorn polymer, and remotely operated emergency isolation valves. The first safety issue is dead leg identification and control. The TPC Port Neches facility had an operating procedure in place called dead legs in high purity butadiene service that was intended to minimize the formation of popcorn polymer. The procedure called for running spare pumps within the unit twice per month in order to circulate material through piping that was connected to the pumps and was otherwise out of service, forming a dead leg. The procedure did not, however, identify the potential for a dead leg to form if the primary pump was out of service for an extended amount of time, which is what happened in the months leading to the incident. Therefore, the procedure did not specify ways to mitigate the hazard of popcorn polymer formation should the primary pump be offline. And the CSP found that although repair of the primary pump was initially prioritized as urgent, it was soon changed to routine due to the existence of the spare pump. This led to a dead leg that existed for at least 114 days, allowing dangerous levels of popcorn polymer to form and grow.
Had TPC's procedure specifically identified the potential for a dead leg to form when the primary pump was offline, personnel may have taken action to prevent accumulation of popcorn polymer, such as prioritizing repair of the pump, purging the piping, or adding popcorn polymer inhibitor to the dead leg. Instead, TPC appeared to consider the offline pump as a threat to maintaining unit operation, not as a threat to process safety, and the result was the destruction of the unit.
In its final report, the CSB made a recommendation to TPC Group to develop and implement a process to identify and control or eliminate dead legs in high-purity butadiene service. In addition, the CSB identified gaps in industry guidance around the issue of dead legs in butadiene units. A guidance document developed by the American Chemistry Council called the Butadiene Product Stewardship Guidance Manual is designed to provide general information to companies that may handle or store butadiene. While the manual gives a general overview of popcorn polymer, it does not contain any information on the potential consequences of dead legs or how companies should identify, control, or prevent dead legs. The CSB believes that such additional guidance could have helped to prevent this incident and could help prevent similar incidents in the future. As a result, the CSB made a recommendation to the American Chemistry Council to revise its Butadiene Product Stewardship Guidance Manual to include guidance on identifying and controlling or eliminating dead legs in high-purity butadiene service. The second safety issue identified by the CSB is Process Hazard Analysis Action Item implementation. The CSB reviewed 2 process hazard analyses, or PHAs, that focused on TPC's butadiene process. In one of them, a PHA performed in 2016, the hazard of popcorn polymer accumulation causing low or no flow was identified. The PHA team made a recommendation to TPC to assure that when equipment is out of service for maintenance, the lines are still flushed monthly. TPC management accepted this recommendation and assigned a due date for implementation in December 2016, almost 3 years before the incident. But the CSB found that the recommendation was never implemented.
Had TPC implemented the 2016 recommendation for personnel to regularly flush piping associated with out-of-service equipment, the dangerous buildup of popcorn polymer that led to this incident could have been prevented.
The third safety issue is control and prevention of popcorn polymer. The CSB found that TPC did not take steps to effectively control or prevent the buildup of popcorn polymer, despite a history of experiencing popcorn polymer formation at its facility. For instance, prior to the incident, in April 2019, TPC began a series of operational trials, including removing a piece of equipment considered problematic from service. TPC also reduced the amount of popcorn polymer inhibitor that was injected into the production stream and used new injection equipment. Soon after the trials commenced, TPC experienced increased popcorn polymer formation within the process. Evidence of popcorn polymer formation was noticed by TPC employees as early as May and June. But in the meantime, TPC continued operating its butadiene unit and did not halt the trials that may have contributed to the problem. And the facility continued to experience popcorn polymer and equipment plugging in the butadiene process, which led to serious operational problems within the butadiene unit. After the extensive popcorn polymer plugging, TPC employees considered shutting down the unit for an unscheduled mini outage to clean up the polymer and make necessary modifications and improvements to bring the unit up to best practice standards. But after clearing several popcorn polymer blockages, TPC ultimately decided to delay this shutdown until 2020, when it was too late.
Popcorn polymer excursions are highly hazardous events. If there are any process vulnerabilities, like unknown dead legs, popcorn polymer can cause equipment ruptures, leading to explosions and fires. Butadiene facilities should develop robust policies aimed at preventing and controlling popcorn polymer. Facilities should also develop policies to shut down units and investigate popcorn polymer formation when it is observed. Had TPC had such policies in place, this incident could have been avoided.
The CSB also found an additional gap in the ACC's Butadiene Product Stewardship Guidance Manual. The manual did not specify conditions that could justify shutting down and cleaning a butadiene unit. As a result, the CSB recommended that the American Chemistry Council revise the manual to provide guidance to help companies identify what should be considered excessive or dangerous amounts of popcorn polymer in a unit, and provide mitigation strategies that operators should take when dangerous amounts of popcorn polymer are identified to control or eliminate the hazard. Finally, the fourth safety issue identified by the CSB is remotely operated emergency isolation valves. At TPC, the butadiene process was not adequately equipped with remotely operated emergency isolation valves designed to stop process releases remotely from a safe location. Had the butadiene process been equipped with remotely operated emergency isolation valves, it is possible that the process feed upstream of the release could have been stopped shortly after the release began, minimizing the size of the initial vapor cloud and explosion. Additionally, any secondary releases caused by the first explosion could have been stopped early in the incident. That step could have prevented some of the subsequent explosions and fires, minimizing the damage caused by the incident. Instead, the unit was primarily equipped with manual and locally controlled emergency block valves, and these could not be safely accessed during the incident, meaning equipment could not be isolated. As a result, severe explosions caused one process tower to propel through the air and land within the facility, and other process towers to fall within the unit. Fires burned for more than a month and led to the ultimate destruction of the unit.
Manual and locally controlled valves are not reliable in a catastrophic incident, since often these valves cannot be safely accessed. Companies that handle large amounts of flammable or toxic material should furnish equipment with remotely operated emergency isolation valves so that potential releases can be stopped from a safe location.
We believe our final report and recommendations will help facilities that handle and store large quantities of butadiene better control popcorn polymer within their processes. Doing so can prevent another terrible incident like the one that occurred at TPC. Thank you for watching the CSB safety video.
For more information, please visit csb.gov.